So next topic will be about quality management for wind energy projects. It's more practical side, coming from the more scientific side, which we heard in the previous presentations. Quality management is based on experience from the previous years, going back from wind farm and wind project developments 25 years ago in Europe, when wind turbines had sizes of 250 kilowatts, which was big in the early 90s. And we had challenges in those days more on the mechanical side, and we saw developments to nowadays multi-megawatt turbines. Which are obviously better managed than computers. Or from time to time. Well, to give you a brief introduction into 8.2, which is not just me, but the group standing behind most of our almost 30 offices, with independent engineers providing service for our clients exclusively in the renewable energy business. And they're mainly almost by 90% in the wind energy business. Well, in fact, my core competence is more the photovoltaics, so hopefully I get reliable numbers and information from my wind colleagues. The 8.2 group started in the early, in the mid-90s, previous century, so we are providing our service for more than 20 years by now. And this is around the world, also mentioned already in the countries where I offered some support for our clients who are in the PV business, where we do it, as I said, mainly in the wind as well. Frame of 20 years is nowadays still the same time frame, but we will hear a bit about the ongoing operation of turbines behind that as well. What we saw and still see from time to time are damages like you see in the background, a full rotor falling down. So this is total loss, or even during operation you see turbines burning off by lightning strike, or even from operational failures. Going a bit more into details, we'll be now step by step. So if you compare the operational conditions for wind turbine running 24/7 almost on different load scales from 0 to rated power, if you compare that to a vehicle which has a lifetime of roughly 100,000 kilometers over 10 plus years, this is the same time roughly which a wind turbine sees in only 2 months of operation. We heard about capacity factor this morning. Tobias mentioned that the capacity factor in South Africa is about 40%, where in Europe and Germany we see 20%. While the lifetime or the comparison of these 100,000 kilometers to 2 months stays the same, but on different power levels here in South Africa. So wear and tear and aging of turbines will be a new experience in this country. In the old days, 2003, we had, if you just split the deficiencies or failure rates from between mechanical failures and electric failures, is more on the electrical side, the red half the left picture. On the right side, it's more the modern turbine, 3 years later. And we have almost a share of 50-50. And in the coming years, so the additional 10 years until today and further on, is more or less the same experience, but on different power scales. Unfortunately, we don't have specific or detailed numbers for the following years. But from the everyday experience from inspections, we see almost the same range of deficiency. So what was it in the so-called old days or early days of wind turbine projects? In the mid-2000s, we had turbine sizes of 2 to 3 megawatts. And we had electrical issues. On the electrical side, well, the generator is something specific, but the electrical side means relays, switches, control boards, and so on. With the mean time between failure of less than 4 years, so 1 to 2 years. In this range, and the mechanical parts stay for some longer, but on the other hand, the downtimes for following on these failures are downtime is here on the right side. For electrical parts, it's very short, just a few days, 1 to 2 days maximum to replace switches or such components. Where the mechanical parts, like gearboxes, hydraulic system, pumps, and so on, take more time to replace or to repair, which means a longer standstill time. Some more statistics may be developed on those numbers. We didn't do that. That is more kind of scientific stuff, which might follow also in this country or might be done by universities. Okay, market trends. What I mentioned already, in the old days we started with small multi-kilowatt sizes, today multi-megawatt sizes. And the trend is still going on, so we have upscaling in power, rotor diameter, hub height, power weight ratio, which is a serious thing because they use squeeze, the reserve for wear and tear to the limit. Still we still develop more advanced power generators, more and more fully automated, but in a harsh environment like high temperature in South Africa or in other countries like Sweden and northern parts of Europe, where the wind is quite strong. We have then snow and frost and all that. So anything can happen in this harsh environment within the generation and conversion of energy, which means you need permanent monitoring and in-time detection to reduce as much as possible standstill times. Because most of the failures occur in high power periods, where you lose a lot of energy if you have standstill. Preventative maintenance can help to prevent from unexpected failures or sudden failures. Independent inspections, additional to scheduled maintenance, which is from half year to 1 year periods, normally need to be added, especially the independent part of the inspection, because the maintenance or operation maintenance service providers are normally linked to the manufacturers. And there's always a conflict of interest. So to get a real clue about the condition of a turbine needs these independent parties. to do inspection with no financial relation to the projects. And from these lessons learned that only maintenance is not enough, we have in the developed markets like Germany and Europe, US and so on, we have these recurrent inspections requested by law, or required by law, to cover and to support and give additional information additional to the maintenance reports. Milestones in the development and implementation phase of wind projects start from the planning. This is just desktop work, site assessments and contracts, where followed by construction, and this means storage on site, transport, and implementation on site, where you may face already hidden failures. Once you started your turbine or your plant, you may find the consequences from improper control of all these steps. During operation, which is the longest phase, normally 20 years, but we will see further operation after that. During this operational phase, you have the end of warranty milestone, and depending on the contract design, the end of full maintenance milestone. These milestones, responsibilities end. Warranty is basically the manufacturer, so the product warranty on your entire turbine. And end of full maintenance means, end of service. And depending on the contract and the options for further and extended contracts, we found that service providers run these turbines down to zero reserve and at the wear and tear. So once the contractor is out of his responsibility and you have a closer look at your turbine after that, you may find it almost close to damage, to full loss. Not always. It depends on the permanent control that you do additionally by independent inspections to see the real status of your plant and every single turbine. Well, further operation means a full review of the single turbine as well as the entire plant. If the technology still matches the requirements by law and also matches the standards, which may have changed after 20 years. But further operation is possible. We see that already as some of our wind plants in Europe already exceeded these 20 years of operation. So, the requirements in these milestones or main phases of the turbine is additional support in the planning and development phase for layout and plant review with sufficient turbine for the site conditions, distances and location of the turbines. During construction phase, you need this monitoring at delivery, but also starting at the packing at the manufacturing facilities. We have this during operation recurrent inspections, which are required in developed countries. As far as I know, this is not implemented in the South African market so far, but might be a topic for a safe and ensured good quality operation for the next years. End of warranty, we saw these two milestones, so there should be an end of warranty inspection as well as an end of full maintenance contract inspection to get the real condition of the plant and every single turbine for any claims against the responsibility. Further operation needs the full review due diligence, which I already mentioned. So, results from the previous years. Older turbines, for older turbines we have experienced for a longer period. That is normal. Younger and more advanced technology, there is less experience, but from our daily work we see almost same challenges on every new development and implemented turbine type. What we found is that the majority of the turbines, which is the bright green here, has no relevant deficiencies. Well, there might be some corrosion at the flanks or such things are minor deficiencies. Some turbines are free of deficiencies, but there is a significant part of roughly 10%, 8 to 10% is relevant or significant deficiencies. Significant means immediate measures are needed to carry on with operation in these turbines. When we go more into detail, the core part of the wind turbine is the drive train, where the energy is converted from wind moving into the rotor until the energy is fed to the grid. And we have electric and mechanical parts converting this energy through to the generator. Sorry. We inspected in these statistics. It includes 208 gearboxes inspected at the age of 5 to 8 years. These were commissioned in the early 2000s, so this is roughly 2010 to 12. Turbines of the size 1 to 3 megawatts for the early days. And we found normal gearboxes. Normal means normal and expected wear and tear, where 8% of the gearboxes needed to be replaced entirely, and 25% of those 208 inspected gearboxes needed repairs. When we go closer to what kind of failures did we detect, this is a statistic about 400 gearboxes, borescopy, this is video endoscopy. All geared turbines, no direct drive, well, we don't have gearboxes at all, you know. So we find impressions on bearings and explications at the toothing part, and also micro-pitting, which is expected to be the early stage of erosion, kind of erosion at the pressure part of the toothing. It appears in a light grayish discoloration on the shiny surface. And these outbreaks then are mixed with the oils and can be found in the oil pieces up to centimeters in size. These are the spikes in the findings of gearbox inspections. This is physical inspection, nothing so far about CMS vibration analysis. What is commonly used nowadays, and lots of manufacturers install their CMS hardware tools on that, but analysis can be done on several more or less advanced software, where 8.2 developed its own one to see whether there's any improvements to other tools available in the market. We have the background from our inspection, so we had also those informations to correlate that with the findings in the CMS analysis. 2.5 megawatt size, up to 2.5 megawatt are the turbines of the early days, up to the mid or end 2000s. The mean size of turbines, onshore turbines today, is above 2.5 megawatts, up to 5 megawatts. Offshore is not included here, which goes much further, but has similar results as we see at the larger 2.5 megawatts. And what you can see very clearly is that the main bearing in the smaller than 2.5 megawatts are almost not seen in the failure distribution. Although 1/3 of all inspected turbines show suspicious signals. It's only 2% in the main bearing, but most of it, 50% in the gearbox, and 44% of these in the generator, which is normally the bearing. So when we go up to 2.5 megawatt, and there's a clear movement to a high failure rate in the main bearings, up to 71%, which is confirmed by 75%, a bit more, after physical inspections. So all these findings from CMS analysis is almost fully confirmed by later physical inspections. The distribution for these main bearings failures to different manufacturers is not evenly. There's one with 40% appearance on these main bearing failures, and others are around 25, 20 and so percent. Don't ask me what is standing behind these, which manufacturer is standing behind these numbers. It's just an uneven distribution there. Okay, what we saw up to now is mainly the failure rate due to wear and tear from the permanent stress, mechanical stress from all those moving parts. What we then have is the rotor blades, which catch the wind to convert it to mechanical power, which runs then into the gearbox. And then we don't have these wear and tear as so, but fatigue from load changes. And if you compare a wind turbine, which goes up to 2 times 10, how do you call it in English? How do you read that in English? 10?
To the power is the power.
Sorry?
To the power.
Okay, so that's 8. That's an 8 here. Okay. And if you compare it with a helicopter, a bridge, or an aeroplane, so airliner, the load itself is less than with the others, but the amount of load changes is far above that. So if we combine this with a higher capacity factor, almost double to Europe, here in South Africa, this might move not further, but up. So we have higher stress and then still the same rate, change rate for the load at the blades. Now we have impacts from insects or from hail or whatever, and if you have additionally erosion from just sand or dust flying in the air when the tips of those blades run at 250 km per hour around, you get results like this. After a few years, if you don't do any maintenance or inspection on your blades and do repair measures as soon as possible. So this is about fatigue on rotor blades. Then we have immaterial damages, which result from failures coming from improper turbine control. And this may lead to a late switching in the generator stages, where you have 4-pole and 6-pole converters or generators, and getting to a higher wind speed, there's a switching to the 4-pole stage, and if that is not properly controlled, you lose some energy on your power curve, and you end up below the predicted power curve, and this is a loss of energy then, and for sure that's a loss of money as well. Other outcomes may follow an improper blade angle, and this can already happen at installation, at assembly of the turbine during construction, which means you never reach the rated power of your turbine, because you have a stall effect on the blade, which doesn't allow the blade to catch the wind at high speed. So this is more these pictures where you have stall effect, so you get improper wind running along your blade, and these might be related to an improper control of the power conversion within the turbine. Okay, summary, challenges and outlook. We find almost 100% of all wind turbines in the market with some deficiencies. Minor, most of the time minor deficiencies, but need action on that side, and just a small percentage, but significantly with serious deficiencies. Upscaling of the wind turbines and the design means squeezing our tolerances of wear and tear, where the limits and the limits for lifetime are stressed, and also the challenges for maintenance are higher than as if you had higher tolerances implemented at the installation of the turbine or in the design. The standard maintenance and insurance cover is mostly seen as fully sufficient to guarantee a 20 years operation without financial losses. And that's not enough, but as I mentioned, standard maintenance is sometimes correlated with conflict of interest. And so from independent inspections, we normally find issues on the turbine that should be addressed to the responsible parties like manufacturers or the maintenance companies, which they try to hide or try to manage by just shorter periods of oil change or such things. So there's a lot of options to just hide failures coming up in the turbine until it's too late. There is a need for additional inspections, which is more or less the same as standard maintenance is not enough. And due to this experience in the developed market, we have these recurrent inspections required by law. Meanwhile, to just ensure also for environmental reasons and to avoid harm, to avoid people that might get harmed by deficiencies and results from failing turbines. Okay, that's the final slide. Thanks for your attention and